It doesn't matter. Not even supposed to be.
Come to the Ericsson side.
Come to the Ericsson side.
No, I'm going to now with the lady. This one looks so small. I compared to mine. It's so huge. I know it is. That's not bad. That's not bad. You can buy a case that comes with a battery, right?
I'm new.
You can be the battery. You're the next right? That's why
That's not true. It's one of the most.
that doesn't take much. You people are not like many. I was
Yeah, switch, take a seat. Excuse me, may I have your attention, please? Okay. So, excuse me, good morning, everybody. So, we are going to start our session of Lwig at IETF 100, and welcome again. So, first of all, because after last IETF, we have done some announcement. Mr. Robert Cratch, who has been serving this working group since its forming, has stepping down as the working group co-chair. And this is our new working group co-chair, Mohit. And do you want to say something?
Thank you to Robert, thank you to Zen, thank you to Suresh for giving this opportunity. Still learning, taking baby steps, so please give feedback if I make some mistakes, or in general, any feedback. Thank you again.
Thank you, Mohit, for taking this job. And then I will go to the note well. Please be aware of this if you are not yet. And we need minutes takers who would like to help. Minutes takers. Okay, thank you, Jan. Thank you. And yeah, please use the Etherpad. And we already have one JavaScriber. Thank you, Bassett. Thank you a lot. And we already hand over the blue sheet along the two lines, and please sign them. Thank you. So this is a brief update of the working group, the document status. So after last IETF, we finished the IoT directorate review and the internet area directory review. Thank you for Charlie and Bernie's view. And for the crypto document, so we finished the working group last quarter, and we have finished the IoT security and the internet area directorate review. And because this is multi-area, cross area work. And we have the TCP for constraint network document, and also the labor management policy document, which is still in progress and will be present today. And I'm also happy to see the update of the Lwig co-op document. Although it's not presented today, but I really like the document, and probably we can seek for working group last court after this meeting. But first of all, so if you are interested in the co-op details, please help to view this document. I think there are a lot useful information in this document. So here comes our agenda for today. So we will basically have three presentations. First one is the TCP for constraint from Carlos, the update of document since last time. And we actually have some discussion on the mainliness about details of document. And because of the co-op TCP standard also in progress in parallel, I think more and more there will be more and more implementations of co-op over TCP, and we'll report those issues to the Lwig or co-op in the coming months. And the second one is the one draft was submitted to the core working group, which is about the security all head of the co-op, which is also quite related to Lwig. So we asked John to present to this working group as well, and see how we can process this document in future. The last one is the library management document from Rahul, and he will give a brief update on document. And I already see some discussion on the 6T working group, also on the similar issues. So any questions to the agenda? Yeah, please. Really? On his side is okay. Let's check which browser are you using. Sorry, yeah, anyway. Any other questions? So I will switch to the first presentation then. Yeah, please, Carlos.
Okay, good morning, everyone. My name is Carlos Gomez, and I'm going to present the last update of the draft entitled TCP Usage Guidance in the Internet of Things. So first of all, let's take a look at the status of the document. So the draft became a working group document after Prague. So thanks to all for the support. And the last revision of the document is version -01. So in this last revision, we intend to incorporate the feedback received in the room in Prague. Also, there was a comprehensive review by Hannes, so we tried to address his comments as well. Thanks a lot for the review. And also there have been many on-list comments by Rahul, Jyotaj, Abhijan, and others. So we also intend to incorporate this feedback in the document. So thanks a lot for the feedback provided. And let's go through the updates in this last revision. So first of all, we have a change in the title itself. So the previous version of the draft was entitled TCP over constrained node networks. However, the new title is TCP usage guidance in the Internet of Things. So first of all, there was a comment by Hannes that this document had escaped from his radar because of the lack of the term Internet of Things or IoT in the title. So we agree that while constrained node networks is a well-defined term in RFC 7228, it's true that the Internet of Things term will allow for a better visibility of the document. And also we have added the term guidance in the title because it somewhat reflects better which is the purpose of the document. So the next update is in the abstract. So the old abstract was still following or according to the original approach of the document, which more like trying to define a TCP profile for constrained devices. However, the new abstract is better aligned with the current approach of the document, where we explain that the goal of the document is to offer guidance on techniques that may allow simplifying a TCP implementation and which are the related trade-offs. And the idea is to help embedded developers with their decisions on what they can configure, choose for their constrained TCP implementations. So we have updates in the introduction section. We have added that there exist optional TCP extensions which increase code size and RAM requirements. However, many of those are not really required for interoperability. Therefore, it's possible to have some careful tuning which may allow to make the implementation more lightweight. And also we have added in this section that TCP implementation following the guidance in this document is intended to be compatible with a TCP endpoint, which would be compliant with TCP standards, although possibly with lower performance in some aspects. Then we have reorganized some of the first sections in the document. So now we have section 3 entitled Characteristics of Constrained Node Networks Relevant for TCP. The new structure for this section is as follows. We have 3.1, which is Network and Link Properties, which corresponds to the former section 2. We have 3.2 Usage Scenarios, which corresponds to former section 3. And we have 3.3, which is Communication and Traffic Patterns, which is a new subsection that has been added this time. And we now explicitly indicate which are the traffic patterns that we consider in the document. These patterns are unidirectional transfers, request-response transfers, and bulk data transfers. By the way, there has been also a terminology change because previously, in the previous version of the document, we used a term like a transactional type of traffic. However, that was somewhat ambiguous, created some problems. So now we are using these terms that can be seen on the slide, which we believe are clearer. Finally, we also state that even if possibly the typical scenario will be that of a constrained device talking to an unconstrained device, it's also possible to have constrained device to constrained device communication, in this case using TCP. Then there have been other updates. For example, in 4.2, which is entitled Maximum Segment Size, there have been updates, however, at an editorial level. So the content is basically the same. However, there has been some redundancy that has been removed. So hopefully the text is now more efficient and clearer for the reader. And section 4.3 focuses on window size. Now we have also added some details here because we already explained before that devices that support a TCP window which is larger than a single MSS window size may benefit from mechanisms such as fast retransmit and fast recovery. However, that requires a window size of at least 5 MSSs. And we have now provided details on which is the reason for that, and also some numbers. So assuming that the MSS is 1220 bytes, the window size of 5 MSS would correspond to 6100 bytes. Then we have also added that bulk data transfers may also benefit from limited transmit, which is a mechanism by which a receiver, sorry, the node that transmits the segments is allowed to transmit new data segments upon receipt of duplicate acknowledgements, and this allows to reduce overall transmission or transfer latency, and it also increases the probability that we can avoid RTO expiration and trigger fast retransmit and fast recovery. Then we have also some updates in the section 4.4, which focuses on RTO estimation. First of all, in the previous version of the document, we pointed to some trade-off, which appears there's some fundamental trade-off with the RTO algorithm, and we basically pointed to some reference. However, now we explain which is this trade-off more explicitly within the text itself, and we basically explain that we can have an aggressive RTO, which will potentially reduce transfer delays, however, at the cost of increasing the probability of incurring spurious timeouts and wasting unnecessarily energy or bandwidth resources. And on the other hand, we can have the opposite behavior, which is having a conservative RTO, which will possibly reduce this unnecessary waste of resources, however, at the expense of a longer transfer delay. Then in this section, we have also explained that the RTO algorithm can have some significant impact on performance, especially when a single MSS window size is used. And we now explain that there's an example on this, which is the RTO algorithm called COCO, which has been defined for CoAP over UDP, taking into consideration the specifics of IoT scenarios. And there's some empirical evidence that at least in some scenarios, COCO outperforms some of the RTO algorithms that have been designed for TCP, however, not specifically considering IoT characteristics. Therefore, this is just one example that there's some margin for RTO algorithm tuning. Then we have also made some updates in the delayed acknowledgements section. So there's a problem when we have a single MSS window sender that transmits data to a receiver that's using delayed acknowledgements. For example, this receiver might be outside of the constrained node network, outside of the scope, not under the control of the entity that manages the constrained devices. And in this case, the problem is, well, delayed acknowledgements is in place. Therefore, the receiver will contribute some delay to the RTT, typically up to 200 milliseconds, but it could be even up to 500 milliseconds. So we have added that there's a workaround for this problem. This is called the split hack, which is a technique used by the micro IP implementation, by which a sender may split the data into two segments of smaller size. And the idea is we transmit the first segment, then immediately transmit the second one. And by doing this, we can really minimize the delay that would appear for the acknowledgement. However, the downside of this is, of course, we have the overhead of transmitting two packets, so this is something that needs to be considered. Then we have also added some content to the security consideration section. We now explain that best current practice for securing TCP, such as using TLS, also applies in constrained node networks. And we also state that security considerations of the mechanisms being discussed in this document also apply. Okay, then there have been also some updates in the annex, which is the section that, as you may recall, tries to collect details on the characteristics of implementations of TCP for constrained devices. And we have some updates in 7.1, which focuses on micro IP. We now explain that micro IP uses this split hack, which is now described in the delayed acknowledgements section in the body of the document. And we have also some minor correction here, because in micro IP, the application is responsible for retransmissions. However, in the previous version, we said that the application must be able to reproduce the same packet. However, that's not correct. What's correct is that the application must be able to reproduce the same user data. And we have also added now for the first time content to the subsection on TinyOS. So we explained that the application is responsible for buffering. There's a send buffer available, and TinyOS supports multiple MSS window size. So still in the annex, now we have added more content to this table. And now, as you can see, we have basically added the details on the rightmost column, which is the one about TinyOS. However, there are still many details which are missing, basically those related with the code size, the data size of the implementations. So please don't hesitate to let us know if you are aware of any of the details missing here, or even if you think we should try to include some additional TCP implementations for constrained devices.
Mohit, this is very useful. In the table, the code size, is it just for the TCP part of that or the whole UIP implementation?
Yeah, that's a good question. I think we need to double check because some of the numbers may refer to the whole protocol stack, some others for just TCP. So you're definitely right that we need to make sure that this is clear and in the document.
And the stars are missing data, or?
Well, the stars mean data that we might ideally find. However, or we would like to be able to provide this data. However, let's see if we are really able to do so.
Hi, this is Hannes. Thanks for the update. It's really useful. On this table, one of the things I thought was missing, or you could potentially add more rows to this or more criteria, because now you have a couple of the implementations look very similar, although in practice they aren't. For example, if you add one that talks about the ability to set up multiple concurrent TCP connection, that could be a distinguishing feature. Also, the issue that you raised on an earlier slide on who is actually responsible for maintaining the buffers, I think that could be a difference. And also, what I was puzzled about is from the description was that pretty much all the implementations claim that they are for 18 and 16 or optimized for 18 and 16-bit microcontrollers. And I was wondering whether there's anything that is optimized for 32-bit architectures.
You meant 8 and 16.
What did I say?
18 and 16.
Okay, 8 and 16, not 64-bit. 64-bit IoT devices. Yeah. Otherwise, I think it's really great. Thank you.
Well, thank you so much for the feedback. So yeah, I think these are very useful suggestions, and we'll try to incorporate them in the table and make sure that it's in the description of the implementations also.
Rahul Jadhav, Huawei. So one of the things that I feel is missing here is whether the stack supports socket interface on top of TCP. For example, I know for sure that UIP doesn't support the standard BSD style sockets. That is a big consideration for any implementer.
Yeah.
Right. So I think that should, for LWIP, it's much easier for applications to write on, applications to be written on.
Yeah, thanks a lot. Yeah, so I agree that this is something useful, and we'll also include it. Yeah.
Ari Keranen also thinks it's very useful work. Thanks for doing this. And few things maybe would be interesting. One is also RAM use. Of course, it depends how many packet buffers you have, etc. But some, let's say, rough numbers on that or intuition would be very useful to understand, like, what kind of things can you actually do with TCP if you have a small amount of RAM. And then another thing, what about TCP over very constrained network, as it's very low bandwidth? Thinking like LP1 scenarios, some chick compression thing. Do you have any numbers on that, or are you planning to?
Yeah, that's an interesting point. I don't have at this moment experience with TCP over something like LP1. However, yeah, I'm aware of some proposals for CoAP, like to better support timers and so on over LP1. So I guess something equivalent might apply for TCP, but I'm not aware of any particular effort in this area. So we might want to consider this maybe at some theoretical level or something like that.
Okay, and then also, I mean, there's no one TCP, but a variety of different options, but also variety of different algorithms you can use it. There's having some more recent one that may be more suitable for that kind of networks, exploring what's the impact and when can you even run TCP, because the classic algorithms start to break when you have very low bandwidth or long RTTs, and what algorithms do you use and what doesn't work when. That would be very interesting.
Okay, yeah, thank you.
So this is Michael speaking. In general, TCP should work well over whatever constraints you have, even for pretty low bandwidth, simply because the mechanism was designed in a time where you had 10 kilobit per second or less bandwidth. So that there are a lot of things where TCP would work for sure. I mean, there can be cases where, for example, we run into timeouts or things like this, and then you need to tune certain parameters. That's for sure clear. We can possibly document it, but by and large, as I'd at least be interested in better understanding so what the issues are, because in general, all the TCP algorithms are adaptive, so they should adapt.
Okay, thanks. And yeah, I was really thinking about, let's say, less than a kilobit per second kind of networks. Could be, let's say, for example, you're at the edge of your NB-IoT cell. You are going very low on your bandwidth. Still have a reasonable MTU, but it's gonna take some time, because you get a lot of retransmissions, etc. So how does TCP behave in this kind of environment?
As I said, I mean, keep in mind when TCP was developed, that was the typical network that you had.
Suresh Krishnan. So there's a couple of answers. Like, so if you put everything into the LPWAN bucket, like there's like quite a bit of variance in LPWANs. And some of these links, I don't think we'll ever have TCP, right? Like, so there's like stuff with like 12 byte MTUs that's probably not going to run TCP, okay? And so I think like we can investigate it, but unless there's like some kind of amazing compression stuff that we can invent, like in the near future, like I don't think it's going to happen. So I take Ari's point, but there's like a subset of LPWAN technologies where this can run, and the subset where it won't, for sure.
Yeah, Gaston, I would like to add that any adaptive technology does have a range in which it works. And as Suresh said, probably not necessarily down to 6 millibits per second, what the speed of Sigfox in certain cases is. So it actually would be interesting to see what is the adaptive range that we can cover.
Did you check what TCP stacks are used, for example, by FreeRTOS and Micrium?
Sorry, used by?
Did you have a look at what Micrium or FreeRTOS uses for in their sort of like as a TCP stack? Because that would be interesting to know. Maybe they already have one of those listed up there, but maybe they have something else, like covering some of the big IoT OSs would be used. Or I don't know what Zephyr uses for that matter. So that would also be. So, for example, with Kyle, the lightweight IP, the original lightweight IP is used, and I think the same is true for the Mbed OS. Yeah, so that may be a way to find out whether the table actually covers a wide range of existing IoT operating systems.
Yeah, thanks a lot.
I didn't check, but it just came to my mind when you had the slide on the tiny OS up there.
Yeah, so we'll check it and consider it as well. Yeah.
Any more comments? No. Yes, thank you.
One last comment. I think one issue that could potentially still be useful to add in the introduction section is to talk a little bit about where this perception about the TCP heaviness comes from, because you talk a lot about the different options, and clearly the ones that you talk about, they add to the bare minimum. But then, of course, there's a trade-off between you add code and RAM size, but then there's also the better performance on the other hand. But if you just stick with the bare minimum, I think it would be nice to say, like, that's what you really buy yourself into. The table provides some of those answers. Maybe double check the numbers. I think they are correct on the code size. Data size is not really, I think you meant RAM size here. But I believe the numbers here are correct. Of course, they're not complete, but I think that's good.
Yeah, so yeah, I agree. We may provide some more insight on this. In fact, there has always been this criticism against TCP, and in reality, many of the arguments against TCP are not valid, or somewhat are issues that can also be found in other reliable protocols. So I agree with that, and yeah, we will try to make it clearer. Okay, which aspects are going to increase complexity? So what is contributing to that? Sorry?
A little bit like myth busting. Because, for example, I read the recent article about why TLS is so heavy, or DTLS is so heavy on IoT devices, and they also claimed you have to support all the 100 cipher suites. If you need support 100 cipher suites, then it will be very heavy, yeah. But nobody says you have to. Like, it was a complete misconception about the way how it works. But the other things that indeed contribute to the size. So I think it would be very similar. Could be very similar here. I think it would be informative for the audience.
Yeah,
Rahul Jadhav, I just want to second that thought. Of putting the design rationale in the document, explaining the trade-offs for the implementers if they are going to ever implement a TCP on top of IoT devices. Because some, like I mentioned before, socket interface, not having a BSD style socket interface is not a good thing, but it reduces RAM, but it has other implications. So yeah, I would second that. Thank you.
Yeah, thank you.
Yeah, Carsten, Hannes, what you said is of course true, but there's a flip side to that, which is when somebody says support TCP, people think, oh, this is going to be a SEC-enabled, aggressive, cubic congestion controlled, whatever thing, and have all the advantages of that. But when we say support TCP, we mean something very different. And that's obviously true of TLS as well. One of the advantages of TLS is that it can interoperate in a number of situations. But when you cut down the support for options like cipher suites, then you also cut down those situations. So the benefit that you actually get from using a standardized protocol is reduced. It's not going away, but it's reduced. So I think that it's really important to keep in mind what we mean by saying support TCP or support TLS.
Yeah, so, well, before, there's one last detail about the references section, which now has been a little bit reorganized with a better distinction on what is normative and what are informative references. And then we've started to consider potential change for the upcoming next version, which will be 0.2. And there's some ideas about possible reorganization of Section 4 contents. Section 4 is the one that actually provides the guidance of TCP over these scenarios. And at least we have identified that maybe we might need to change the order of some subsections. For example, the one about delayed acknowledgements is possibly more relevant in the end than the ECN one, so possibly should appear earlier in the section. And we are also considering, although this is not well developed yet, other approaches on how to structure the kind of guidance, such as maybe guidance for single MSS situations, guidance for multiple MSS, window size, and so on. So, well, these are just some early ideas on possible changes for the next version. So that's all from my side. I don't know if there may be any further comments.
Thank you, thank you. And for I see a lot of valuable discussion during the presentation. I think probably Rahul can contribute some text, or Hannes, if you like, to the point you just raised. Thank you. Switch to the next
one. So I'm John Mattsson from Ericsson. This draft has been committed to core as an input to the work there. It has never really been presented there. Just maybe a single slide in some other presentation. Okay, yeah. That better? Yes. Yeah, can hold it. That's probably best. Good. So this is an analysis of the overhead of different security protocols used to protect co-op. And analyzed protocols are DTLS 1.2, DTLS 1.3, TLS, OSCore. And then DTLS and TLS are analyzed with and without compression, and two different compression algorithms, both the standardized generic header compression, and then also another suggestion from RASA that was never standardized, included for comparison. And then DTLS is analyzed with and without connection ID, and also how compression works when you include connection ID. Connection ID is a quite new draft for DTLS. And what's analyzed here is the TLS and DTLS record layer. The TLS handshake is not analyzed. And here is the major overview table. We'll go through all the parts here. As you can see, DTLS 102, as you probably know, has 29, and the analyzed cipher suit here is ASCCM 8. Hannes?
I'm curious on why you specifically focus on the sequence number aspect, like.
Just to give an overview, it obviously the compressed overhead depends on the sequence number. TLS and DTLS uncompressed does not, but to give a good picture of how the compressed, then it's heavily dependent on the sequence number, of course.
I would have started the slide by saying, like, here are different algorithms, and the size of the header obviously depends on the algorithms rather than focusing on a sequence number or.
Here is a single algorithm, CCM8. I think that's what basically people are using. So basically, if you choose a column here, you get good comparable numbers for overhead for that algorithm.
Okay.
Yeah.
Okay.
And here's an overview of why TLS and DTLS 1.3 gives less overhead uncompressed. Here is the TLS 1.2 header, gives 21 bytes overhead when you have 8-byte MAC. DTLS 1.2 added epoch and sequence number an additional 8 bytes, but did not remove anything because the nonce is needed for example, CBC cipher suits. DTLS 1.3, as it only uses AA, this remove the nonce again, and we only have epoch and sequence number. And
there are also two types of content types. So there's the header types in DTLS. Did you look at that as well? Or is that in a subsequent slide?
These are only header type version.
Okay.
17. Yeah.
Okay.
Uh,
Because there's a new in the latest document. There's of the DTLS document. There's a optimized header format which removes version and content type and compromises compresses the epoch and the sequence number.
Okay, yeah, that I have not looked at. I missed that. I will have, but that's a very good comment. I will add that to the next version of the documents. That's heavily relevant. Added. So yeah, as you can see, DTLS 102 has quite large overhead. TLS and DTLS 103 has significantly less, but not really small. But the good news is that compression works quite well, and then you get significantly lower numbers. So what you get, first we have this. This is a stateful compression algorithm. Then it provides a little bit more better compression than the generic header compression, but on the other hand, it has state. It's also not generic. It does. Now Rasa updated it for DTLS 103, but it doesn't work for TLS, for example. It doesn't work for connection ID. So we'll focus more on the generic header compression. And typically value for, and these are somewhat dependent on different parameters. Here the parameters are chosen to give representative values for a sequence number of 1 byte. For example, if you take the number 1, you get significantly less, which is not representative. But this is close to the very close to the average. Can confirm that the generic header compression works very, very well for DTLS 103. You get even less overhead, just 14. And the main reason is that DTLS 103 uses the same version number as DTLS 2. And basically, the dictionary in generic header compression is just a DTLS header for a handshake application. Generic header compression also works. It works quite well for TLS. But as you can see, you get 3 or 4 extra bytes. And the reason here is that the dictionary in GHC is a DTLS, includes the DTLS version number and so on. You could probably get, there's no theoretical reason why you would get, so another dictionary to GHC would probably squeeze it down to this. You could probably come up with a dictionary that does both. But yes, Carsten?
Yeah, we had a lot of foresight when we did this because we put the TLS 1.2 version number in there, and that's now eternal. So TLS 1.3 has the TLS 1.2 version number.
No, it does. Okay.
Or the TLS working group has taken the generic header compression into account. Now, that was actually not the reason, but.
These are the numbers you get. I use some, there's an implementation of the generic header compression on GitHub from Freie Universität Berlin, which I use for this. See, and then see if I have some more things. No. Then OSCORE, new security protocol, currently is in working group last call in core, has built in from the beginning very compact format, gives compare even smaller than TLS, DTLS and TLS compressed, and responses are similar size. They don't depend on sequence number.
Can you explain why that is?
Yes, that is because OSCORE reuses features it relies on co-op. So co-op matches the request and the response based on the token. And then OSCORE uses sequence number. It finds the context based on the token instead of sending them in band as DTLS and TLS does. And then also OSCORE uses CUSI, and CUSI uses CBOR, and CBOR encodes numbers dynamically with a small length and value. So you don't have this fixed 6 or 8 byte sequence numbers, which without compression takes a lot of space.
Which of course is a little slower. Like here, OSCORE seems good for traffic analysis because you can judge from the response that it's a response, like from the size of the response that it's a response.
Yeah, you can probably see that from the direction you're sending the packages.
Well, don't say that because you can send it in both directions.
So here's, I think I'm running out of time. Here's an example of the OSCORE header, not going into that. And then I also tested DTLS compression with connection ID. As TLS gave much more, I was afraid that GSC would not work optimally with connection ID, but I can happily report that it does. Basically, the compressed overhead only increases with the so connection ID includes a new it includes a new field in the DTLS header, and I did some test, and it seems like it always, the compressed overhead always just increased with the length of this connection ID, which is optimal. Yeah.
Yeah, Carsten again. I'm not sure whether that was meant as a joke or a serious thing, but I think
Please closer to the mic.
I think we actually have to take this as a serious comment and look at what the impact of compression is on visibility of information. So of course, when you compress parts that are in the clear, first of all, it looks like it doesn't make a difference. But if there is a lower layer compression below that, a lower layer encryption below that, excuse me, then this means you still might see something through that encryption that you're not supposed to see. So that's maybe actually worth a little bit of attention.
Yeah, that's definitely worth attention. Shown that compression of variable bit codecs, you can basically find out what people are saying with like 70% of the words. So that's
yeah, there has been some padding features added to TLS 1.3 to make traffic analysis more difficult.
Yeah. So yeah. So that's what I have to say. This is currently in core. Would be happy to transfer it for Lwig if there's any interest here.
Thanks. Maybe you should change the title of the document because it makes like it gives the feeling that security adds a lot of overhead. Like, oh, yeah. What's the best way to get rid of that overhead? I have some ideas.
Yeah. Do you have? Yeah, good point. Do you have some suggestion?
No, I don't have. But you know, I can just I can already see some articles that say all this security is just comparison. Yeah, comparison of
comparison. Yeah, that's good.
Yeah,
I don't want to definitely want to say that.
That was Ari's suggestion. Or Jaime, yeah.
But it seems there is interest in the group for this work.
Yeah, Ari Keränen, yes, I think these kind of things are very useful outputs of this group. I mean, like having actual numbers you can point to in a lot of discussions. So what is the impact of doing X on this kind of IoT scenarios? So I think it's very useful work. And I'm glad to have finally a reference with comparison of the numbers, because these kind of questions you get asked a lot. Like, hey, if I want to run TLS, DTLS, something else, what's the impact? Not overhead, not impact. Thanks.
Okay, so the next step for the authors is to submit as a Lwig document.
So, Gastmer, maybe one comment on exposition that is related to calling this stuff overhead. I mean, there is some useful information in there. It's not all overhead. And I think the numbers would be easier to understand if you would separate the information that essentially cannot be compressed, such as the authentication tag, from the other information. So, I mean, you need to send those 8 bytes. There is no way around that unless you use a different cipher suite. So I think it's not right to say that there is a protocol overhead of 13 bytes. The protocol overhead is much smaller, but then there's also a security cost, and that's those 8 bytes.
Yeah. Now I think I used the exact. I just copy pasted from 7,400, but that's a good point.
And Ari Keränen, also the handshake was not analyzed in this document, right?
No, that's not included. There are some work on comparing TLS and ad hoc in ACE working group. I know that Jim Chad has done some analysis, but that's not public at the moment, and I have not been.
Okay, so maybe, I mean, maybe having a pointer to whenever that document becomes public in this document would be useful. So getting the full picture, because usually the handshake is the dominating factor.
I think just having numbers of how large TLS pack. I don't think there is any easy to find numbers on just how large are the TLS packages in the normally in the handshake, or what can I do to slim it down?
Well, one problematic thing is that you included this sort of work by Rasa. It's great work, but it didn't go anywhere. So it may lead to the wrong conclusion that it may actually be available somewhere. But I think it was not just proposed, but then it was not picked up and was not continued.
Yes.
The other thing on the handshake comparison are more complicated, because here you are comparing apples against apples, because you want to accomplish the same thing. There are some differences, as you pointed out, and I'm not sure those are in the drafts with, and also the remark that Carsten made is quite important, because most of the overhead is actually caused by the security algorithm itself. But the handshake, the challenge there is you quickly compare apples against oranges, because if you have different properties and different design goals, then what does that actually mean? As we have seen in some of the discussions, you want to have certain backwards compatibility with existing middle boxes. With some new work, the middle boxes are not yet there, but maybe then in the not so distant future. And so it's really tricky.
So in the interest of time, can we be concise? We have one more presentation, and I don't want you to be here for lunch.
Okay, then quick comment. Should we have a document documenting these trade-offs with different kind of handshakes, different kind of algorithms? You don't want to document handshakes?
I think it will be published in some other group. I'm not planning to add that to this document at the moment, but I think it's useful. I think it will come out of ACE in some form. Yeah.
Okay, Rahul, next.
It's all right. Hello everyone. I'm Rahul Jadhav, and I'm presenting the 6LoWPAN neighbor management policy. It's specifically applicable for multi-hop networks on 802.15.4 networks. In last IETF, after last IETF, this work was adopted, and while renaming the document, we also made some changes to the text. But essentially, we stripped out some text, which was some detailed explanation. So we thought it might not be necessary. But there were no technical changes as such to the document. So before going into the details of the updates here, I wanted to give this background about how constrained operating systems are getting developed. most of the times the consideration is given to reducing the number of packet buffers while designing a constrained operating system. For example, let me take an example of Quantiki, where you have a single send and receive buffer to reduce the amount of memory size. What I'm trying to say here is there are other things which are occupying more memory and has also a bigger impact, especially in multi-hop 6-low-pan networks, and which has to be dealt with when you give design consideration for such implementations. So if you see here like an example of routing table, well, routing table doesn't come into picture for non-storing mode of operation, but still this is one of the biggest component. So till the moment you are trying to work out with like smaller networks like 10, 20, 50, 100, there's no problem. But the moment you go into sub-gigahertz where there and with large number of nodes in the network, the density increases and you need to have a bigger neighbor table. And if you see, the neighbor table size can actually reach something. This is what it has reached in our implementation. So it has reached almost 6.5 KB. While the packet buffer is like we have a packet buffer which is used for both send and receive. It's only 1280 bytes. So why neighbor management? I just want to go into the details of this. So if the network density increases, especially in case of multi-hop networks, you have a lot of neighbor cache entries getting filled up because of the routing childs, routing parents, because of the authentication sessions. And how do you manage these entries? So if you're not able to manage these sessions, these entries properly, you'll end up losing routing adjacencies, eventually increasing the routing convergence time, and the network will simply keep flip-flopping between the paths, and there will be a lot of overhead added. The control overhead in the overall network will be very high. So this is where, currently if you see, most of the implementations are, they use trivial policies, LRU and FCFS, which are not optimized. So here is a sample. So this shows the kind of network density. In some cases, the network is really dense. In some cases, it is sparse. So here, if you see, this particular node is taking all the load, but it might be limited with the space, and then eventually all the node might flip-flop to another parent node, and you essentially want to get a network which is sort of balanced. Wherever the memory is available, the network should switch to that place. So the specification or the current draft takes into consideration the authentication session as well, which is very important because authentication sessions also occupy neighbor cache entries. So so these are the cases where the neighbor cache entries. So these are the cases where the neighbor cache entries will be filled. So it's a routing parent, routing child, authentication in progress, and there might be some other sessions also which might be needed. So there is an others section that has to be that might also show up here. So we have some signaling recommendations for neighbor cache management. While we don't provide any new changes to the protocol, so in case of non-storing mode of operation, in case of storing mode of operation, do you really need to send NS? Do you really need to send NS with ARO option? Or with the recent update to 6775, do you really need to send ERO option? So these are all the things that have been discussed as part of signaling recommendations in this document. The proposed policy is that we have reservation-based scheme. So we have so the basic principles on which this draft works is, if at all there is an eviction, how big is the impact? So based on the impact of eviction, the categorization is done. I'll give an example here. If there is an eviction of a routing child in the parent, then all the subsequent grandchilds are also, there's an impact to those nodes as well. So that's a big consideration there. The insertion reason needs to be kept along with the neighbor cache entry. This reason will help eventually to decide the lifetime of the neighbor cache entry. For example, in case of authentication sessions where the authentication is still in progress, to avoid DOS attacks, you might want to keep we want to reduce the amount of lifetime that is for this neighbor cache entry. So these are some of the, so this is basically the proposed policy. So whatever I've just discussed and whatever has been talked about in the draft is reactive. We want to go to a proactive. There are some problems with the reactive policy. The primary problem is if, let's say, for example, you advertise some information, the child nodes joins a parent node, but after some time, and it sees that the parent node doesn't have enough resources to join. But after and it switches to another parent, but after some time, the same parent sends a new DIO, and then it switches back to the same old parent, and that does a failure signaling again, and then it again gives a status saying that it is not, the resources is not enough, and then switch back. So there's a lot of flip-flopping happening there, which we want to avoid, but we don't see any other way other than to change something in the routing protocol for this. There is some proposition already in the working group, role working group in context to this, but right now, I don't know if it sorts of takes into consideration this particular factor.
Please rush to the end.
Sorry?
We're running out of time.
Oh, all right, okay. I'll just have one more slide, I guess. How do we? Can you go to the next slide? Okay, we already have a proprietary implementation in place. Contiki implementation is in progress. Contiki lead authors are part of this work, and we intend to. I mean, the current draft already, whatever the current draft says, it's already implemented. Our proprietary implementation takes into consideration even the proactive part that I just mentioned, but is not part of the draft. So that is something we would want to work upon. That's all from my side, and really I would appreciate some feedback from some reviews from the working group towards this problem statement. Thank you. That's all from my side. Any questions?
So we are running out of time. Any questions? Okay, so we can hand over to the list. Thank you, Rahul.
Thank you.
Thank you. The meeting adjourned.
Nobody wants to leave. Perfect.